Okay, so day 3, we are finally putting it all together here. Notice our list of things that we are doing. Actually, domain could probably be listed first, and then we probably want to look at that before we identify a hole in our graph, because domain includes everything that was ever in my denominator. The only thing that we are changing on here, or adding, I should say, is slant asymptotes. And we're going to talk about this in just a minute, but these two, if you guys remember this phrase, are mutually exclusive. You can have one, but you cannot have both, okay? So as soon as you recognize that you have one of them, you eliminate the fact that you could have the other. You'll never have both a horizontal and a slant, and that's because they come from categorizing. Little over big, big over little are same. Well, it can't go into two different categories, so it'll only ever be one or the other of those. So putting this all together, to draw a slant asymptote, we have to remember how to graph something like a linear equation, y equals x plus 3. Slant asymptotes will always be linear equations. This is, if you remember, that y equals mx plus b format. So when we do this, remember that m stands for your slope, the number in front of x. B is your y-intercept. That the first thing we graph is this, and that it is a dot on our y-axis at whatever number that is. The second thing we graph is our slope, and that we think of as a fraction. If it doesn't look like a fraction, we can always put it over 1, right? And we want to think of our slope as a fraction because we want to think of it as rise over run. The number in top is how far up or down we go. The number in the bottom is how far right and left we go. So if I were to graph the example given, y equals x plus 3, our first dot would be on our y-axis up at positive 3. If there is no number in front of x, it's a 1. If my number in front of x doesn't look like a fraction, I make it look like a fraction by putting it over 1. And that tells me that I'm going to go up 1 to the right 1 to find my next point on the line. On your slant asymptotes, you're going to want to do that all the way across your graph. So I went up 1 to the right 1. I also did the exact opposite of that, down 1 to the left 1 to finish out the other side of my graph. And that is a topic we probably want to talk about. If I were to have that fraction 1 over 1, I can make it, as long as it's still a positive number, you can make the top and the bottom both negative as well, because those would both cancel out to be a positive, right? On a different note, if we were to have a negative fraction, let's pretend our slope had been negative 1/2. This is a common mistake people make. When you have a negative fraction, remember that negative can slide to the top or it can slide to the bottom, but not both. Because if it was both, it would simplify down to a positive number, right? So negative 1/2 is the same thing as negative 1 over a positive 2 or a positive 1 over a negative 2. And you can graph both of those fractions, but you can't put a negative in both spots at the same time, okay? So keep that in mind as we are graphing these linear equations. All right, so our first example does have a slant asymptote, and we'll talk about that when we get to that section here. First function is f of x equals x squared plus 2x minus 8 over x plus 3. The first two things we look at before we get to the whole horizontal and slant asymptotes, which is our kind of new topic today, is holes and vertical asymptotes. So that's why we're pausing here and finding those first. Remember, when we handed a function, the very first thing we're going to do is factor. And look to see if anything simplifies. I don't have anything that matches top to bottom, so this does not simplify, which means there is no hole, NA or none. We identify anything that is missing as not being there. Our vertical asymptote is making our denominator anything that makes our denominator equal to 0. And there is no set number of these. Remember, we could have multiples. We could have 1. In this case, we have 1. So we set our denominator equal to 0. All asymptotes have to be written as an equation. This is a vertical line, so x equals negative 3. We go draw that dotted line.
So are your vertical asymptotes always going to match your domain restrictions?
The combination of your vertical asymptotes and holes. Yep, will always match your domain restrictions. We didn't have a hole in this one, so like you don't see that part of it, but the combo of those two things will always. Yep. All right, so now our new topic, horizontal asymptotes versus slant asymptotes. Remember, at this time, we look at our fraction and we categorize it. Is a little over big, big over little, or same? On Friday, we talked about a little over big and a same. Automatically, little over big has a horizontal asymptote at y equals 0. Automatically, a same over same has a horizontal asymptote at whatever the ratio of the numbers in front of x is. What we did not get to see is when it's a big over little. First of all, that means it does not have a horizontal asymptote. It does have a slant asymptote. So we're going to talk about how do we find that today. Now up there I have that we're going to divide and ignore the remainder. Technically, you get the option to divide using long division or synthetic. I will always show synthetic division. Okay, so we will do synthetic division and divide the top of the fraction by the bottom of the fraction. We're going to ignore whatever remainder is there, and then we're going to take our answer when we divide, and we're going to write it as an equation. And that equation will always be a linear equation, y equals mx plus b. Okay, when we get to that point, and then we go back to what we just practiced at the beginning today. How do I graph something in y equals mx plus b? That is what then my slant asymptote will look like on the graph. So let's go back to our problem here. And I kind of summed all that up at the top. It will happen when the top of our fraction is exactly 1 degree higher than the denominator. We will divide to find the slant asymptote. Now, look at how I have this written. We factored it on the first one, but in order to divide, I want to go back to the unfactored version because I need the numbers in front of my x's here to put into my synthetic division. So use your unfactored. Use the polynomial, x squared plus 2x minus 8, using the 1, the 2, and the negative 8. We are dividing by the factor x plus 3. Remember, this is the factor, so out front goes the 0, negative 3. Negative 3 times 1 is negative 3, plus 2 is negative 1. Negative 3 times negative 1 is 3. Gives me a negative 5 here. You will always ignore whatever this number is. Ignore the remainder. We will take this and write it into our equation y equals mx plus b. 1x minus 1. There is your slant asymptote.
So you're always going to have a vertical, but then it's going to be either horizontal or slant.
Yes, except for on our rare, like, we'll see one at the very end that has kind of an exception to having a vertical, but like 95% of our functions will have. But you can never have both a horizontal and a slant. You'll either have one or the other. Okay, so this one does have a slant, y equals x minus 1. We go graph that. So again, what we practiced, y-intercept starts at negative 1 with a slope of 1 over 1. You'll see that I don't put dots, I put little dashes because it's an asymptote, and so asymptotes are drawn as dotted lines. Start at negative 1, up 1 over 1, up 1 over 1, all the way across my graph. Back 1, down 1, all the way across my graph would be my slant asymptote. That's the only new thing today. Questions? Divide, write your answer in y equals mx plus b, and graph it. The rest is just the rest of our steps here. Okay, so after we have that graphed, we go find our x and y intercepts. So to find my x and y intercepts, I'm going to again want to consider this in the factored form. It makes my x-intercept easier. So kind of bouncing back and forth between factored and unfactored. It's the same thing. We didn't simplify anything out anyway. Your x-intercept, remember, is going to be anything that makes our numerator equal 0. Well, we have two things that would make our numerator 0. If x plus 4 equaled 0, or if x minus 2 equaled 0. So we have two x-intercepts in this problem. We have an x-intercept at negative 4. We have an x-intercept at positive 2. Remember that you can have multiple x-intercepts. You can have, there is no number of x-intercepts. You could have 0, you could have 1, 2, 3, 4. There is no particular number. You can only have at most one y-intercept, and we get that from just plugging in 0. So I would go back to the original if it was me. You can plug it into the factored form, but all we are doing is plugging in 0. You have one and only one, if at all, y-intercepts. So this would give me 0 minus 8 is negative 8. 0 plus 3 is 3. That would be the point 0, comma, negative. And I always find it easier to graph those if I think of them in mixed numbers. So 8 divided by 3 is 2 2/3. So a dot on my y-axis at negative 2 2/3. Questions? Okay. To finish out the problem then is testing out any additional points that we were to need in any part of our graph. Now I know it looks weird with the slant asymptote that's on there, but remember that we always break our graph using our vertical asymptote. So if I were to look at, again, just breaking my graph using my vertical asymptote, your vertical asymptote is here. If I look to the right of that, I have 2 points, and 2 points is enough to draw my graph. So we will do just like we did on Friday. Follow our asymptote, go through those 2 points, follow our asymptote. That would be the shape of your graph on that side. On the left of our vertical asymptote, we have 1 point. Now, I've been advertising that we want 2 points on each one. It's a good check for ourselves. We're going to get used to the shapes here of our graph and probably not need 2 points always. But let's go ahead and test an extra one. So if I were to test like x equals negative 5, I already have a point at x equals negative 4. So if I test out x equals negative 5, again, I'm just plugging that in. You can plug it into this one or the factored version. It doesn't matter. 7 on top. Seven over negative 2, which would be negative 3.5, which looks like it goes right along with the point that's already on there, right? It's to the left of that line above our slant asymptote. So then I follow my slant asymptote, go through those 2 points, follow my vertical asymptote, draw my graph. On Friday, we talked about general shapes that we would expect to see. And we talked about like if there were outer parts to our graph that we expected that they would be a sharp corner all the time, or a corner. And if it was on the inside, that it could either be a cubic or a parabola. Remember, we kind of talked about those general shapes. Okay, well, you have 2 general shapes that you can see when we've got a slant asymptote. One of those looks like we see on the board. And to me, that kind of looks like our corners, but like flattened out a bit. Like it doesn't like corner, right? It kind of flattens out a corner here. The other possibility is this. You're going to see that one, but you could also see something that looks like this if we were to kind of draw a very similar graph with a vertical and a slant asymptote. Instead of seeing like the flattened out corners, you actually could see these like kind of squished parabola looking things in there. Okay, so those are the only 2 shapes you're going to see when given a slant asymptote, and they do not mix and match. So either both of them are flattened out corners, or both of them are squished parabolas. And if you get like 1 and 1, something went wrong. You shouldn't have one of each. They should both be the same shape. Okay? Questions? Okay, we're going to try one more start to finish, and then we're going to look at some weird cases. So this one shouldn't be any different than the one we just did. I'll let you guys try this one, and then we'll look at some weird cases here to make sure that we don't get caught off guard when something unique comes up. Yep, opposite of the factor. This thing. Little over big, big over little, same. Those 2 have horizontals. If it's big over little, it has slant. Big over little. Okay. The first thing I started doing is I just factored to see if it has a hole in the graph. It does not, and I would leave them sitting right next to each other because sometimes it's easier to work with it in the factored form, sometimes it's easier to work with it in the not factored form, so you can kind of bop back and forth. It's the same function, but I do need to identify for myself that there is no hole in this graph. Nothing crosses off. After a hole in the graph, we would go to any vertical asymptote that we would have. This one does have a vertical asymptote, and vertical asymptotes come from anything that makes our denominator equal to 0. Set my denominator equal to 0 and solve. We would have a vertical asymptote at x equals 2. And then we go to our decision, horizontal versus slant. And again, that goes from categorizing your fraction, little over big, big over little, or same. Now, if I look at it in the factored form, it's easy to make a mistake and say it's the same x to the first over x to the first. But remember, if I were to multiply that out, it's really an x squared over an x to the first. So just be careful if it's factored. This is a big over little. Big over little is a slant asymptote, which means you cannot have a horizontal asymptote in this one. Slant asymptote comes from dividing. Go back to the unfactored version to find your slant asymptote. Our process, do your synthetic division. Remember, you will use the opposite of your factor, so a positive 2. It doesn't matter what the remainder is because we ignore it. We take those numbers and we write them into our y equals mx plus b, y equals 1x plus 3. And we graph that equation. Give yourself a slope there if you need to remember that it's 1 over 1. So I start my equation up at 3 with a slope of 1. Draw that all the way across my graph. Questions so far? X-intercept, what makes my numerator 0? We have two pieces to our numerator. The factored form is a little bit easier to see on this one. If I were to set my numerator equal to 0, I would have a x-intercept at -4. I would also have an x-intercept at +3. So we have two of them, -4 and +3. And again, you can list them as the numbers or as ordered pairs, which would be -4, 0 and 3, 0. Your y-intercept, we plug in 0. I think the unfactored version is easier to plug that into, so I get 0 plus 0 minus 12 is -12. 0 minus 2 is -2, and that simplifies down to a +6. And again, you can write it as 6 or 0, 6. And then we have to test any extra points if we need them. To the left of our vertical asymptote, so here's my vertical asymptote. To the left of that, I have 2 points. Draw along your asymptotes through those 2 points along your asymptote. That graph's good. To the right, I would probably test one more point just to make sure everything is good. We've already got a point at 3, so I would test out x equals 4. If I plug 4 in here, 4 plus 4 is 8. 4 minus 3 is 1. 4 minus 2 is 2, which would give us a point at 4, 4. Slide along my asymptote, go through those 2 points along my asymptote. A slant asymptote is just like a vertical asymptote. You cannot cross a slant asymptote. So if your graph was trying to lead you to cross, like you had points on either side of a vertical slant asymptote, just like a vertical one, you are not allowed to cross that.
Can you touch it without crossing?
You cannot. You cannot.
Are there not going to be any holes in slant?
There can be. Not on the 2 examples I had up here, but there could be a hole in it. Yep. Our domain, our only domain restriction was x cannot equal 2, which is where your vertical asymptote is, -infinity up to 2, and 2 to infinity. All right, I have 2 kind of unique cases. We may or may not work through the whole thing here. One of the unique cases is, what if part of your fraction doesn't factor? Okay, now, like on this one, if you were to look at this one, and step number 1 is to factor it, well, there aren't factors of -8 that add up to 1, are there? Your options are 1 and 8 and 2 and 4, and no combo of those would give you a +1 answer, right? So, okay, what if it doesn't factor? Well, first of all, that probably means nothing's simplifying out of our fraction. Great, move on. So if I fly through this one, there is nothing to simplify. There's no hole in this graph. Vertical asymptote is unaffected by this. I just set my denominator equal to 0. There's a vertical asymptote at 1. This is a big over little, which means that it is a slant asymptote. We would divide. Since I'm just kind of flying through this one, remember, I will show you 1, 1, negative 8. We are dividing by a positive 1. We don't care what the remainder is. Our slant asymptote, y equals 1x plus 2. And then we would move to our intercepts, and this is where it will end up catching you, is on your x-intercept on this one. I am supposed to, for my x-intercept, set my numerator equal to 0 and solve. Well, quadratics, we have two options to solve. Factor and set them equal to 0, or quadratic formula. We already talked about this one is not factorable. So we would have to do our quadratic formula on this. Now, one of two things will happen. It'll be an ugly decimal if it is not factorable. Which is exactly what happens on this one. When I set this one equal to 0 and solve, I get two answers. My two ugly answers are, if I'm remembering correctly, something like 2.4, and then I do the negative version and get like negative 3.4. Okay? They're just ugly decimals, but it doesn't change what I do. I still put those dots on my graph. So we had a vertical asymptote at 1. We had a slant asymptote up at 2. Okay, and then we have intercepts at 2.4 and negative 3.4. They could just be ugly. That might be one of the things that happens. But what if, instead of that being factorable, it was not factorable because it was something like x squared plus 16? Well, when I set something like that equal to 0 and solve, I end up with x squared equals negative 16, and I'm square rooting a negative. Okay? Which means my x-intercept, pretending this was finding my x-intercept, is imaginary. If I run into that, I did my quadratic formula and it came out imaginary. Guys, what that means is your x-intercept is imaginary or doesn't happen. It would not hit your x-axis. What would that look like in this picture? That would look like something that would go like this and like this. Notice that never hits our x-axis, and that can happen, so I don't want you to be caught off guard by that. You might run into a problem where your x-intercept is imaginary, which means you have none, and it looks something like the green graph up there. Okay? All right, this is our last one. This is a special case. You will see this one happen again on your worksheet, so that's why we're going to do this problem together. And then you'll have something to follow on your worksheet. You'll see this, I think, 2 more times on this worksheet and then 1 more time later. We'll always come back to this example here. So our last one today, f of x equals x squared plus 4x minus 12 over x minus 2. We start the same. Factor. So factors of negative 12 that add up to positive 4 would be positive 6 and negative 2. And this is where this one is unique. Not the factoring part, or even the first part. It does have something that simplifies, right? We've seen that before. That means we've got a hole in the graph. Okay, that hole in the graph, we set what we crossed off equal to 0 and solve, and that gives us our x value here. Well, when I solve that, I get x equals 2. What is left over is what's unique. What is left over is x plus 6 or x plus 6 over 1. Doesn't really matter how you write that, but it doesn't look like a fraction anymore. So this unique case happens when we simplify and no fraction is left. Okay, so we simplified it, we got rid of the entire denominator. It doesn't look like a fraction anymore. Okay, well, what ends up happening is we end up just graphing that line, y equals x plus 6, with a hole here. That's all that it ends up looking like. Now, I'm going to talk through exactly why it looks like that. And finish this one out. Remember that we get the y value from plugging that back in. So 2 plus 6 or 8. We have a hole in our graph at 2, 8. Okay. Now we really could find the rest of this like we always have. Our vertical asymptote is what makes our denominator 0. Well, our denominator would be 1. Nothing is going to make our denominator 0. So this is kind of that special case where we don't have a vertical asymptote. This is about the only time we will not have a vertical asymptote. Otherwise, we always have a vertical asymptote. This is the special case also. If it simplifies down to a linear, you will not actually have any asymptotes. So I can go through. I do understand that this is a big over little, but if it simplifies down to a linear equation, your graph ends up being the same as your slant asymptote. So you don't have one. Okay. Your x-intercept, what makes our numerator 0? If I set x plus 6 equal to 0, that would be -6. My y-intercept, plug in 0. 0 plus 6 is 6. Or just graph the line y equals x plus 6 with a hole at 2, 8. It looks like a line with a hole. Questions on that? And it does have a domain restriction that is at x minus 2. And I get that we simplified out, but again, domain restrictions, if it was ever there, it is there. So your domain on this, negative infinity up to 2 and 2 to infinity. That will be the same as number 4 on your worksheet. So when you get to number 4, maybe you start with number 4 because we just did that problem and it's going to be kind of your unique case. That is what you are going to match it to.